Well, thank you for joining us this evening. My name is Royal Hansen. I run the Privacy, Safety, and Security organization at Google, but probably more importantly, graduated from Yale in '97 in Saybrook and majored in computer science. We were few but mighty at that stage. I think it's sort of amazing in talking to Dean Brock to see what the department has become, and maybe you'll talk a little bit about that. Just quickly, we're super excited to have a good mix of people from industry, from the academy, interested parties, from alumni, from Google. Thank you for joining us. And Dean Brock and I, as we've gotten to know each other over the last year or two, he pointed out to me, and I think we actually have a dual-hatted in Mariana, someone who'd been in the department and at Google, but these relationships between individuals is really where we think the magic and sort of opportunity is, working either on projects or problems together. We have some examples of that, which we'll talk about today, but we would like to think that this is the beginning of more of those going forward. Dean Brock's going to give a little bit and introduce the panel, and then we'll do about 20 minutes of some Q&A after they talk about what they're doing. And then we'd love to take questions for 20 minutes or whatever it takes from the audience. So start thinking about it now. Great.
Thank you, Royal. Okay, thanks, Royal, very much for hosting us in this amazing event space. And thanks to the panelists for coming and joining us. You know, it's been something of a dream of mine just to have a kind of a LCD screen with the words Google and Yale Engineering on the same. I mean, really, like, that's actually pretty impressive. So in and of itself, I think we've accomplished quite a lot tonight. So yeah, I mean, what Royal says is really right. I've spent a fair amount of time working in administration at Brown and now at Yale, and always the efforts of administrators to come in and foster university industry collaboration sort of are fraught, right? I mean, it's how do you force people to have conversations across these boundaries? It doesn't really work. So the best thing to do, and this really comes from the mathematical culture that I come from, is just to try to get people in a room together, you know, with nice snacks and coffee, and let them take the initiative and them sort of start the conversations. And it's amazing what happens when you just provide that opportunity and some nice, you know, Hagoromo chalk and a chalkboard, if that's what you're into, which is, you know, the way the math works. But, you know, at Yale, there's sort of a catchphrase, which is, you know, it's been working for 320 years, so why do it any differently, right? And there's been a little bit, I would say, of an aversion or an allergy to opening our doors to exciting work that's going on in industry, or even at the, you know, in the national labs and things like that. So to get that going, you have to sort of break through some walls. And I'm really, really excited to have been given the opportunity to work with the sort of renaissance of engineering and these exciting faculty, and to meet folks from Google who have a sort of a like-minded approach. And I've always felt that about Google as a culture, that it has sort of an academic strain running underneath it. They're willing to support and willing to evangelize the idea of basic research in the service of discovery that might ultimately translate into something that's exciting for industry. So with that said, I'm excited to introduce the panelists, and I will begin with my colleague Ruzica Piskac, who is a professor of computer science and is no stranger to Google researchers here. Ruzica's research focuses on using formal techniques to improve software reliability, specifically the concept of privacy-preserving formal reasoning. To my immediate right, Ben Fisch is a new faculty member in engineering, relatively new. And his interests are found in cryptographic verification as a process of checking and attaining information, but also as a powerful tool to build highly secure software systems. He's interested in applied cryptography, distributed systems, blockchains, and cryptocurrencies. And Nina Taft, whom I just met, is a senior staff research scientist at Google, where she leads the Applied Privacy Research Group. She received her PhD from UC Berkeley, go Bears, Over the years, she has worked in the fields of networking protocols, network traffic, matrix estimation, internet traffic modeling and prediction, intrusion detection, recommendation systems, and privacy. Nice to meet you. Amanda Walker, whom I also just met, is a well-known leader in the security and privacy community and was one of the early security and privacy pioneers at Google. Over the course of her 13-plus year career at Google, she built some of the key systems, teams, and initiatives in the security and privacy areas that we depend on today. All right, so Ruzica, I will let you start, and I guess Royal is going to moderate a discussion after a brief introduction from all of them to their research. Here you go.
Great, thanks. Go ahead.
Okay. So, no, I think I don't need.
We have mics.
Yeah, we have mics.
Yeah, I have mics. So. Thank you for the introduction. So I will give just a lightning talk about my research area and the new directions that we are pursuing. So my research area is formal verification, and the goal of formal verification is to prove that code is correct. To do that, we use formal mathematical foundational techniques. So to kind of give you a big pipeline, it's like you take the code, you convert it into mathematical formalism, let's say a formula or a graph, and once you have that, you actually use automated reasoning techniques to reason about that. So having this pipeline, and to kind of paraphrase what Tim Brock just says, like if it has been working for a couple of decades in industry and well applied, why to change it? And what I want to show you today is like two new exciting directions that my group is pursuing. One is to add AI and LLMs to the reasoning about and formal verification, and the other one is also to add security and privacy. So to kind of give you a bigger picture, let me start first with the LLM-based techniques. In verification, in order to be successful, naturally it has to scale. So it's to scale, like if you usually will hear like, we want to prove millions of lines of code. But to work for these millions of lines of code, you really need to have some way to infer something called program invariance. And this has actually been one of the bottlenecks of verification. People tried various techniques. People tried synthesis, mathematical analysis, and so on. But what my group is doing, and there is a student who can wave and show that he's the one behind it, we are actually developing a new techniques that actually use AI-based techniques to develop new invariants and then help verification to scale to directions that were actually not seen before. Now you can see maybe, do we just want to use LLMs and AIs as a tool? But I actually want to say that they are beautifully complementing the work that is done in verification. Because if you think about, if I will tell you, okay, use LLM for something and you will get the output. And you will say like, no, I don't want, there is hallucinations, I don't know about correctness. But what we are doing also, there is my collaborator from law school, actually what we are doing is we are taking output of the LLMs and then we actually put formal verification techniques and we actually show that the output is correct. So this is actually something when we think about what are the new directions that we can go, one of them would be also how to improve legal reasoning. But now, since we are on the top on the panel which talks about privacy and security, let me also mention a little bit about privacy and security that we are doing. And I actually want to give also the credits here to Mariana, because that is the work that we started with our joint student Ning. And what we are doing, like, is remember the pipeline of the verification. Code, you convert code into formula, you show that things are correct. Now imagine this is your private code, and I'm asking you like, okay, is yours correct? We're now in two different parties. In order to verification to work, I will need to show you the code, and actually then we can proceed with verification. But what if you want to keep your code, your data? You can see that there are various other applications private. In that case, like all this does not work. So what we actually learn from cryptography field is that on the top of the verification, you can add various techniques from cryptography, something like zero-knowledge proofs, I think multi-party computations, and then you can achieve this pipeline to be fully, like private and secure. Now, you can also say, if you're not cryptographer like I am, like, what is this all about? Like, can this be applied to other things? And maybe let me give you a simple example. Many of you have bought a house or apartment, and you know how many papers and convincing things you need to do to convince the other party. Yes, only to say 1 billion. Like, yes, I have enough funds to buy the house. So in a zero knowledge settings is that a similar situation. You have something that you you know, and you want to convince the other party using cryptographic primitives, using something which is mathematically founded, that you indeed have this knowledge. So it's, and this is what we are using to kind of ensure that we have private and secure verification. And now to conclude, it's not only that we can use this for verification. Together with Mariana and HIP, we started the collaboration in using this also for compliance checking, because if you have several parties and you want to check compliances, you don't want to reveal the data, so that can be used. And then we can also extend this towards direction of the planning, of the scheduling, and similar other techniques. So this is like what I want to show, yes, verification has been here for several decades. Why to change it? Because it's the right exciting time, and we can add many new techniques to kind of improve it. So thank you.
Okay, so I'm Ben, and I work on cryptographic verification, which, whereas what formal verification does is it catches when developers introduce bugs into programs. Cryptographic verification is for when you don't even trust the machine that the program is running on. We rely increasingly so on computation that's done for us, right? And as an end user, we're quite removed from the program. We need to trust that the program was written in the right way and it's doing what it's supposed to be doing. And that's where formal verification helps, right? Because even as the developer, we think we wrote something that is doing something that we intend for it to do, but it may not be doing that. Right? But with increasingly complex computations, now with LLMs and all kinds of massive computation that's not done on our own computer and it's done somewhere else, and in fact it's done in places where then many millions of end users are all affected by the computations that are happening in one place, it becomes increasingly difficult to trust the machines that are carrying out that computation. Right? Not because we don't necessarily trust the companies that run those machines, but those machines could be hacked.
That's the right answer.
if you hack a machine that's running some kind of inference, some LLM inference or other kind of ML inference for end users, and you could cause a lot of damage, especially when it's being used in now healthcare applications, all kinds of sensitive things. And so the type of work that I do allows for end users on their phones to run a very, very small program that could verify the correctness of a extremely complex large computation. So you can have, a massive farm of GPUs, right, running, on Microsoft servers, Google servers, somewhere else, and computing the result of some model, and then a small program running on someone's phone can in milliseconds check that the computation was done correctly, even if that machine was compromised by some malicious attacker who's trying to mess with the results. And so that is, this goes back to one of the what some people think is one of the most fundamental theorems in computer science, called the probabilistically checkable proof system, which is came out in the 90s and was completely theoretical, and over the past decades we've turned it into something that could actually be done. And so this has, on the theoretical side, the fact that we can do this has tremendous implications in computer science and foundational, for the theory of computer science. But today, these things are actually used in practice. They've been used. They've been used primarily in the blockchain world, and now we're looking at using them for being able to verify the results of ML computations. And so that's what I and my students are working on now. These computations are exceedingly complicated, and to create this succinct small proof of correctness that can be verified in a few milliseconds requires a lot more work than doing the original computation. So all the work that we're doing is trying to bring the extra work that you need to create this succinct proof of correctness down, right? To be able to also distribute that work and run it potentially over many machines. I'll say one more thing, which is that the ability to do this also enables us to decentralize computation. When you have things like LLMs that require a massive amount of work to be able to train, there are very few companies in the world who are able to provide those services. And that leads to an oligopolistic structure. And maybe today it may not be such an issue, but we could worry about in the future if it's not competitive enough, then that puts a lot of power in the hands of a few providers. And it's always been talked about how you could crowdsource computation. There's so many computers around the world. Anyone with a GPU could contribute a little piece of work to training a complex LLM. But that doesn't really work because you can't trust random machines around the world. If people contribute pieces of work, first of all, why are they going to do that? You're going to have to pay them to do that. And if you pay them to do that, then they'll start giving you bogus results and collect the payment. So if you can verify that the computation that people did was correct, you can now verify that these little pieces of work that all these machines around the world are contributing to this one massive cohesive computation are all correct. And so suddenly you take something like crowdsourcing and actually make it possible and realistic. Now, this is something that is, it's not practical to do today at the scale that Google and Microsoft are able to train models, but we're working towards making this practical.
Good. Okay, so I'm Nina, and Amanda over here runs a large research organization covering all of privacy, security, and safety. She'll give you the overview, but I run one of the teams in that org. And we are focused on systems work and applications of machine learning for privacy. So I like to tell people it's ML for privacy, but I'm not doing privacy for ML. Mm-hmm. So I think probably most of you know the difference. Just to give you some examples of the kinds of things we work on, we work to find creative uses of ML that will help in the privacy world. So for example, we try to give nudges to developers, so like third-party developers on the Play Store, so that they will be better citizens of privacy. And for example, Google launched a very cool product actually about 1.5 years ago called Checks, meant to help third-party developers as they develop their apps. And Checks can look at the code, and it can look at the privacy policy. And my team did the work on automatically analyzing privacy policies, because we have a lot of NLP experts on the team. And if you find a discrepancy between what the code's doing and what the policy says, we tell them, before they launch, right? So this helps developers to have higher quality privacy policies that actually correspond to what the code does. So analyzing privacy policies was something we were working on for a long time. We also do a lot of work on fingerprinting. So I don't mean taking pictures of your finger here. I'm talking about websites that will try to fingerprint your browser and trying to detect when it's going on. And we have it's a hard problem. It's been around for a long time, but we have some cool solutions recently that we can work with, even if there's obfuscated code. The scripts are not visible. We have some tricks to work on that. We also use our NLP stuff. There are some legitimate use cases of fingerprinting, but websites have to declare it, in their privacy policy on the website. So we check, those kinds of things. We're looking to try to identify intent and when it's legitimate, because that's really the hard part of sorting out, like when it's okay and when it's not okay to be doing that. I guess the other thing we do quite a lot of is text analysis. Now we're using the latest LLMs. Here we're focused on analyzing text that people write, so be it in Reddit or in app reviews or in our own Google feedback channels. We can analyze what people write about privacy, but also what they write about trust. We've even built classifiers for ambiguous things like what's benevolence, and security and abuse. And we pull all that out. And that helps us to give feedback to the teams. What can they do to improve the product based on what users are asking for? So yeah, we've done a lot of work on analyzing app reviews, and I'll leave it at that. When you have a tool like that, it's a purely machine learning tool, but it helps people who actually want to do user studies. It's really a sort of a new tool in the arsenal for people who try to study users. They do user studies and surveys. This is a different way to understand users. It has a different set of, pros and cons, but it really allows you to analyze, millions and millions of texts. There's no limit. So you get scale, but there are other trade-offs. Like you can't go back and talk to a user and say, what did you really mean? You know, so I'll leave it at that.
All right. And I'm Amanda Walker, and as Nina noted, I oversee a large organization of applied researchers in privacy, security, and safety. Our mission is basically find new tools, develop and discover new tools to add to the toolbox. Sometimes this is applying pre-existing techniques to new problems. Sometimes it's applying new techniques to old problems, kind of a combination. Some examples of that are for cryptography. We have a bunch of cryptographic researchers who've been looking at applications of cryptography to problems besides basic confidentiality. So multi-party computation, private operations over data, so private set membership, private set intersection, private linear regression, things like that, where there's a calculation that one or more parties want to do over data, but the naive way of, well, just share all of your data and do the calculation has difficulties. You know, it might be legally prohibited. It might be, you know, you don't want to disclose your trade secrets, you know, as in the formal verification example. And so how to perform useful functions on data without disclosing it is a major sub-theme. So we also have a group working on fully homomorphic encryption, and not just the theory, but building tooling for it so that engineering teams can go try it out. Say, okay, I want to take my code and figure out, you know, if I can do it in the encrypted domain. And this turns out to be a hugely engaging tool. It's not entirely practical yet. We had a team who took a machine learning algorithm for detecting objects in video and compiled it with the FHE transpiler and ran it, and it ran, and it worked correctly at a CPU cost of 60 million times. So some of these things are still, you know, showing that it's possible is one thing, making it practical is another. Another theme is applying ML and AI techniques to privacy, security, and safety problems. Nina did a great overview of what her team does. We also are doing things like applying deep learning to side channel discovery in hardware. So can you build a deep learning model that monitors the power consumption of a chip and can extract information about the calculation it's doing? Turns out yes. We recently published a paper and published the model for this. I think, I'm trying to remember what it's called, GAMP? Something. Anyway, it monitors the power of a chip and can extract crypto keys from common cryptographic algorithms like AES and ECC. We have teams working on the other side, which is, can we do machine learning and AI in this encrypted domain? A lot more speculative, a lot more performance problems to be overcome, but every year we're able to do more, faster. We've had a number of things recently where we can do things with less computation, but more accurately. So it's a very interesting set of problems. At the other end of the spectrum, on the user side, there's stuff like Nina's team's been doing with looking at user sentiment about privacy, feedback for applications developers. We also have a team looking at risk users, how they reason about privacy and security and the features of the products that they use, and how that differs from, say, your average Silicon Valley engineer. So Sonny Consalvo and Patrick H. Kelly, who are both here, are essential in that area. And all of these things play into where we go with the technology. Sometimes it's new technical tools, sometimes it's a better understanding of how users are interacting with it, how it's affecting society. So we kind of cover this very broad range here.
All right, so there's our table setting. I'll ask a few questions, and we're sort of halfway through. If you start to think of things, and maybe we'll warm you up, so think of your questions. But you know, Ruzica, when we first met, one thing that struck me is, you know, in my world historically, there were always you know, we were the security teams for banks. If you call old colleagues here and I worked inside of banks, and we were notoriously the cobbler's children in that we would try and keep the business secure, but we were not always very good at using the best technology for these kinds of problems. And what I loved about our initial conversation was the idea that you could use large language models, even in this emergent state, to solve problems like formal methods, which are notoriously hard to scale.
Right.
Reminded me a lot of what we're doing, and Nina, you said a few of the same things. Can you talk a little about what that's like in the current environment with these models changing and advancing, modalities changing? Do you have the expertise? Do the people have what the compute they need? Like, what's it actually like to work through this?
To answer this, I mean, when we started to work in this problem, I mean, even at that time, machine like LLMs were, like you only had they were not as powerful as they are today. So which means that we started with combining okay, we will just use them as a tools. We would see what we get, and then I remember when my students said me but these results are really rough, right? That was literally the word that he was using. So getting the results was actually meaning that okay, we would kind of use this because we were trying to use LLMs to derive invariants of the code, and then we would say okay, it's not really correct, but we get a correct feeling how correct they are. So we would encode them and then put them to additional solver in order to kind of get a proper solution. And then once we would get, initially we would have to build several pipelines in order to make this scale and to work properly. And I think these days we actually are getting nicer results because the reasoning capabilities are improving, but actually the paper that we are planning to hopefully submit tomorrow is actually saying the following, that when we were playing with LLMs, imagine, we kind of showed that you can add something that you as a human would actually immediately detect, but actually they can be there to confuse. Maybe let me somehow show you examples how you can easily confuse LLM. Let's say if I say from true follows something, you as a human would say yeah, everything follows from true. But now if you would say from true follows true follows true follows true follows something, you would say okay, it's all the same. But now let me actually add a little bit complications here in the truth. might say things like, if I have one apple and you have two apples, then we have three apples. That's true. So I will put it here. Then I will put another such statement instead of true. So once you do this chaining, you actually realize that LLMs are still just transformers, right? And we will still need to rely on formal methods because then you actually can detect that things that you as a human would detect it's really the same. LLMs cannot because they're transformers. And that's why we somehow still need to use formal methods. We cannot just say okay, let's kind of put everything to LLM and everything will work beautifully. We still need to use reasoning and formal methods. So,
how does that relate, Amanda or Nina, to what you've felt at Google as we've tried to use these new models for the similar?
Yeah, we had some examples where sort of naively applying an LLM to a problem and giving it a task. It did a terrible job.
Yeah.
Hallucinations left and right,
yeah,
etc. We found that if you give it good examples and instructions, and this is the kind of thing we're looking for. Here's an example, etc. It got much better.
Yeah.
This then leads to the question of okay, this is in effect a human doing some of the reasoning part and priming the LLM for it.
Yeah.
Right now. Yeah, that's what we have to do.
Yeah.
This whole new field of prompt engineering is essentially that.
Yeah.
Is there a step beyond that where there can be more automated reasoning about it? A lot of the work in formal methods seems like it should play in there somehow, but it's hard to figure out how to connect it yet.
So let me just add to that. I think, so there's also a lot of bit of work, and I forgot to mention this, but that my team and others are doing on creating synthetic data, right, for training. That's nice because you don't have to use user data. You've solved one privacy problem from the get-go. But some of the tools that we are building are smart in the following way, which related to what you're saying, that when you see a model and you try to figure out the mistakes that it makes. And it can study the mistakes that it makes. And then we generate more examples of synthetic data exactly kind of in the vicinity of those mistakes. So it allows the models to train better on the hard cases. And it sounds like that's a little bit what's needed here, right? Like we have to understand the hard cases, and then we need a lot of data about those cases.
This is also what we need for not only for verification, but we have a different project where we take text and we try to convert it into first-order logic, right? And like if you would, as you said, like if you just throw it blindly, you get something that looks
it looks plausible.
It looks plausible, and then like. Yeah, could be, but then it does when you give it to the solver, it doesn't even compile, and then you actually start to analyze a little bit, and then exactly we did what you suggest, like let's give the cases, let's do prompt engineering. We actually tried so many different techniques. We tried techniques which would be let's try to have some sorts of internal representation on which they're better trained. Maybe we will get better results because if we know what is internal representation, we can just write compiler. It went somewhere, but then we kind of came to this problem which leads us to the paper that we want to write tomorrow, which is okay, but there is the reasoning problem, right? So that's, it's, I kind of find them that they're very useful tools because they're really useful, but do I trust? No. But do I want to use them? Yes. But I want to put things on the top that I want to trust. So,
we're all going to need a copy of this paper by the end of the night. Distribute it.
Well, I see my students sitting in the audience, so I don't know whether they're working on the paper.
Working on it tonight or not. Okay.
Good luck. Lots of coffee.
Ben, let's sort of switch gears. If that's using LLMs to solve some of these problems, when you talked about the distributed computing in terms of crypto, it reminded me of some of our work in federated learning. But that whole, we're going to end up in a world with on-device activity for some things, cloud activity for others, and third-party in the way Nina's talked about. How do you string these together when they're really born of different approaches? Do you see the federated learning approach in what you're talking about in a distributed ledger kind of a model or distributed computing?
Right. So what I'm looking at is proving that computation was done correctly, even if it's done on an untrusted machine. And an example of that was the example I gave, where you have many different machines spread around the world that are all contributing a piece to a computation. That's what I call decentralized, training services or inference services. Now, federated learning came out of a desire for more of a privacy-motivated desire, where you have the data that's used for training is originating in many different machines, and you don't want to put all that data into one place. You would like to train on the data where it originated on, and not put all this data into one place. And you want the training process in a way to preserve the privacy. The federated learning approach. In the cryptography world, we try to get extremely strong guarantees on privacy. We try to say that there's a concept of multi-party computation, where if you have many different machines contributing to a computation, they all have private inputs, then you do some computation, you get a result. Anyone who's observing the result of that computation, or anyone who else involved in this computation, should not learn anything about the inputs of the other party, to the extent that they could, any information that they learn, they could have simulated on their own. Right? And so there's a very strong notion of privacy called multi-party computation. There are also efforts, and my students and I work on this as well, to have this additional privacy guarantee if you have a decentralized process of training a model on data originating from different sources. Then you want to have a guarantee that you end up with some kind of certificate that the computation was done correctly, that you trained the model correctly, even if you don't trust the individual machines that were involved in the computation. And you don't learn anything about the information other than the model. Of course, you can infer data from the result of the model itself. Right? The model has learned the data in a way, right? And it's a separate problem to figure out how do you how do you monitor what questions people are allowed to ask to that model? In certain settings, you may not. If it was trained on patient data, for example, it's a completely separate, also very interesting problem to figure out how to limit the information that researchers can get from studying the data collected from patients. But multi-party computation protects the privacy of the inputs that went into training and ensures that the only thing that we get out of it is the fully trained model.
I think the thing that's interesting about is that you talk about these sort of personal relationships working on problems. When I came to Google, what struck me is at the scale of what we do, it becomes challenging to in a performant way, practice some of the things that you're talking about. And I think there's a real opportunity to string those things together in efficient ways. And a few examples of that already.
Right. The main challenge of these cryptographic tools, which are very powerful, both for privacy, multi-party computation for privacy, and cryptographic verification, or otherwise known as succinct proofs, are that they're extremely expensive to create relative to the original computation, right? And people care about privacy, people care about security, but when you ask them to spend a lot more money for it, then you see how much people really care. So, right. So the big challenge today is to make these cryptographic tools cheaper. And one way of making them cheaper as well, I mean, there's also cheaper in terms of the dollar cost of computation isn't that high, but if computation is sequential and it takes a long time, that's another type of cost. So making these computations highly parallelizable.
Yeah.
Ruzica?
So, yeah, I wanted to follow up on that. So what we did, again, what Ben rightly pointed out, the problems are when you think about zero-knowledge proofs, right? They're too complex to use, and they're also too expensive to use. And one thing that we noticed, it wasn't really going into succinct, snarks. We were actually looking at when you have multi-party computation involved. So one thing that we noticed is that proofs can actually be easily parallelized, right? Because if you think about, let's assume I want to compute two functions, something is you apply first function, then you apply the second function. If you have two parties involved for zero knowledge, that means I will first have to convince you that I did this part correctly and then I did the other part correctly. But internally, I already constructed this proof. So what we did, we actually says okay, we will kind of create this proof. It was somehow similar to the live variable analysis, so people who are speaking compiler. And then what we did was actually, we found a way how to parallelize proofs. And then actually, there is still price to pay, what you said, and this is the price that you actually have to pay in compute, right? But you'd gain time. And then we kind of even use the buzzword which says we actually prepare proofs which are cloud ready. Good buzzword. But in this way, you actually, yes, eventually you always have to pay the price, but you can actually save time, but you will have to then put things on the cloud or somewhere else where you can.
That's okay. Thank you for joining in. We'll keep going here. We got time in the end. Thank you.